Hey guys, Ms. Gosling here. In this video, you're going to learn about alternating current. By the end of the video, you'll be able to define alternating current and describe how it is generated. So let's go ahead and get started. So there are a few very important components of an AC circuit. First of all, we need to have a rotating coil. You can see here we have a rotating coil that's being turned by a hand crank. This coil can be turned by a lot of other things as well. So for example, some of you may have seen there are those treadmill batteries where you run on a treadmill and that generates a current. In that case, your running is what's going to be turning that crank and moving that coil. We can also talk about what is a little bit more of a more common generation of power by looking at something like a power plant. In a power plant, what we're doing is often we are generating steam, which is rotating a coil and generating an electric circuit as a result. Anywho, key initial component, again, is that rotating coil. Second, in an alternating generator, we need to make sure that we have some kind of magnetic field. Here, that is being generated by the two halves of a magnet. Of course, magnetic fields can be generated other ways as well, but this is a nice, simple way to generate one. So, third, we need some kind of motion between the coil and the magnetic field. And again, that rotation is what's causing that motion. And then finally, in order for our generator to be worth anything, it has to connect to the outside world, of course, because we don't want to just generate current for the sake of generating current. We want to generate current to run important things like computers and lights and cars. So here is our connection to circuit components. So we can use our generated current to run some sort of electrical machine. So these are the general components of an AC generator. And when we're talking about alternating current, what we are talking about is instead of a DC current, which is going to be some constant voltage, what we are looking at is an alternating voltage. So our voltage is going to have maximum and minimum EMFs over time as the coil rotates and as it moves in relation to that magnetic field. So the more coil that is perpendicular to the magnetic field, the larger the magnitude of our EMF. And of course, the less coil perpendicular to the magnetic field, the smaller the EMF. And when that coil is parallel to our magnetic field, as it actually is in this picture, we're not going to have any EMF at all. But since it's continuously rotating, it's going to continue to have changing EMF, hence alternating current. Okay. So these are general components of an AC generator. We've also talked a little bit about what an alternating current actually looks like. And again, it's going to look like a sine wave or cosine wave as our coil moves in relation to our magnetic field. So let's look a little bit more at an AC generator. And here, in the bottom of our picture, you can see the relationship between the coil and your magnetic field. So when we're all perpendicular, we're going to have a maximum. When we are parallel, we'll have a minimum. And so you can see that in our graph here. On the y-axis of our graph is our induced EMF, or that curly E. On the x-axis, we're going to measure time, since our EMF is changing over time. Now, I do want to talk about a few of the components of our sine wave that can change. So, first of all, we can change the frequency of our rotation, so we can change the speed of rotation. And so when that happens, the period is, of course, going to change as well. And so say we have half the period, we'll have half the frequency. And so what's going to happen is our sine wave will condense. So we're changing the frequency of rotation to half what it is. Then we're going to go through a full cycle in half the time that it took us with our initial graph. So that is frequency equals 2 times the frequency of our graph. We can also increase the magnetic field or the number of turns or the area. And all of those three things are going to change our induced EMF. So if any of those, for example, doubles, so if we have twice as many coils, twice as large an area, or twice the magnetic field strength, then the maximum and the minimum EMF will also double. So those are the things we can see on our graph. We can see that the ways that our field strength, our rotating coil, the number of turns, and the larger coil area, as well as the speed of rotation, can all affect the alternating current that's generated by that coil and magnet. So now let's take a moment and talk about how we can measure the magnitude of a current. So as you know, when we have a DC circuit, so if we have, our battery here that's hooked up to a resistor of some kind, we can measure the voltage on the battery by putting a voltmeter across the battery. We can also put a voltmeter across an alternating current generator. But what we're going to get is a graph of current versus time, or EMF versus time, that looks like this. So we're going to have that sine wave. So you might say, okay, well, we'll measure the output by taking the average value. So current equals current average. Let's see what happens if I do that. So I can measure the approximate current that I have here for 0.5 seconds. I can take a current here, and I can figure out how much time I'm spending with all of these different currents. However, if I do that, what I'll notice is that my positive currents and my negative currents have the same magnitude and opposite signs and are going to cancel out. So that would just tell me that for any alternating current, my output is 0. So that's not very useful, right? Because I can't use that to compare different alternating current generators, since they all have the exact same average. So I'm hoping you guys can see from here that our problem is that we have both positive and negative values of current, and that our current will be moving in one direction initially, and then back in the other as our coil rotates relative to that magnetic field. So to get rid of that negative sign, we're going to have to talk about our power. So remember that power is measured as I squared times R. So what that means is that our power is going to look something like this. So what we're doing is we are squaring our y-axis values. And so we get 0.5 squared, which is approximately 0.25. We can have 1 squared, which is 1. 0.25 squared again, or 0.5 squared again, which is 0.25, and so on. I'm assuming here that our resistance is 1. So when you look at this, all of our power is positive. And so now it's actually useful to measure the average value of our power. And in doing so, what we will get is we will get the measurement of the strength of our alternating current generator. And so we're getting a really useful value that helps us compare one alternating current generator to another. And in fact, we are going to measure our alternating current value by using the equivalent direct current that delivers the same power as the alternating current over one cycle. So what that means is that a lamp supplied from a DC circuit, so if I have a light bulb supplied from a DC circuit, and I supply that from an AC circuit with a current from an AC circuit with the same power reading, then what I will get is that that bulb has the same average brightness as my bulb in a DC circuit. And what I will find is that for any AC circuit, the average power is equal to 1/2 times the maximum current squared times the resistance provided by my load. And I know that if I were to have a DC current that provided the same power, then that would be equal to I squared times R. So our R's are going to cancel, and what I'll get is that the current that DC supply would have is equal to the square root of I squared over 2. Sorry, I max squared over 2, or I max divided by the square root of 2. And we are going to call that the root mean squared, or RMS current. And this is how we will be measuring current for our alternating currents. So instead of taking the average current, what we'll be taking is the root mean squared current. And we get that by using by talking about the equivalent DC power that would cause me to have the same average power as my alternating current. So, to summarize, here are the 3 equations that we will use to measure the output of an alternating current generator. So first, we can measure the power of our alternating current generator by multiplying our root mean squared values of current and voltage. We are going to define our root mean squared current as the maximum current divided by the square root of 2, and our root mean squared voltage as our maximum voltage divided by the square root of 2. And it's with these values that we can use to compare one alternating current generator to another, and therefore use them and talk about them in a meaningful way. So let's go ahead and look at an example. So in our example, we have a coil rotating at a constant rate in a uniform magnetic field. The variation of the EMF with angle theta between the coil and field directions is shown. On the graph below, add the EMF that will be produced when the rate of rotation of the coil is doubled, and explain your answer. So just so you guys know, you would be giving a written explanation, of course, for this kind of problem. I'm going to go ahead and just explain my answer as I draw the coil out. So the thing that's really important to know, of course, is that EMF is negative N d phi by dt. So what we are doing is we are increasing the speed at which we go through one rotation. And in fact, we are doubling it. So we are going to go through, we'll go to 180 degrees in half the time that it took us before. So we'll go through a full cycle between 0 and 180 degrees now, because we are speeding up. So again, our coil is rotating in half the time, and so we will go through 2 cycles in the same amount of time. Secondly, my coil is rotating faster. In fact, it is rotating twice as fast. So that means that d phi by dt, that my change in magnetic flux over time, is also doubling. So what this means is that the amplitude of my graph is also going to double. So again, my period is halved and my amplitude is doubled. And that's going to give me a graph that looks something like this. And again, my graph is not perfect, but this is a pretty clear explanation of what is going on. So let's go ahead and look at another example. The diagram below shows the variation with time t of the EMF generated by a rotating coil. Calculate the RMS value of the EMF and the frequency of rotation of the coil. So let's go ahead and get started by calculating the RMS value of the EMF. So when we're looking to find the RMS value of the EMF specifically, what we're being asked to find is VRMS. So again, if you see EMF, you should automatically think you are finding your voltage root mean squared value versus your current root mean squared value. And for this, we are going to use the equation. So we're going to use VRMS equals Vmax over the square root of 2. and we can read our maximum voltage from the graph. So if I go to my maximum point here, I can go over to my y-axis and I see that Vmax is equal to 100 volts. So that's going to give me that Vrms is equal to 100 over the square root of 2, which I can leave as is, or I can stick into a calculator to find an actual numerical answer. I'm going to leave it as is for the ease of going through this problem. So second, we want to find the frequency of our coil. And to remember how to do this, you guys are going to have to go way back to last year and review topic 6. So in topic 6, circular motion, we learned that frequency is equal to 1 over period, or 1 over the time it takes to go through one full cycle. And looking at my graph, I can see that one full cycle takes me 20 milliseconds. So my frequency is 1 over 20 times 10 to the negative third, or 1 over 0.02. And that is going to be the answer to the second part of my question. And again, I can stick this into a calculator and find an actual number, or I can just leave it as is, which is what I have chosen to do. So what you guys have learned here is how to use a graph of our EMF over time to learn more to gain information about the AC current being generated. So let's go ahead and talk takeaways. So first, AC current is generated using either a moving coil or a moving magnetic field. In our example, we just looked at a moving coil. Remember, what we care about is that relative motion. So if the magnet is rotating instead of the coil, we are also going to get an alternating current. Second, you learned that alternating current is measured by the power produced, which we calculate using the root mean squared value of the current and or voltage. And I also just want to mention that we can also use IRMS or VRMS as values of our AC circuit. However, the power is perhaps the most pure way to do this. Anywho, you guys have learned now about alternating current generators and how they work and how we measure them. So now it is your turn to try solving a couple of problems. Best of luck and happy solving.